All right, now. So this is all about the ice cream lab. Now, ice cream labs are supposed to be fun. Okay, everybody enjoys eating ice cream. This might. Oh, that's a good point. You have tabs that you're supposed to have in your ring binder, and I said yes, we have 14 of those, right? So 10 of those are for all the units of instruction in this class, right? Then you need one tab for all of your references. You already have one reference that I haven't told you where to put it, but the one that has all the equations with the values for the delta H, that's the reference. So that should go in your references. And then you got to have a tab for labs. So this might be best placed in your lab section of your ring binder. Now, if you don't have it labeled yet, that's fine. Let's just take the notes. We can get it done later. But you should know that lab handouts, okay, and lab instructions that we don't put in your lab notebook go on behind a tab in your ring binder called labs. Okay? All right. So the ice cream lab. So I want everybody to moan really loud for me right now. Moan. 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 No more now. That's it. That you're done. No more moaning. Okay? No more moaning. All right, because what I'm about to tell you, something I'm going to moan about it. I want to hear it. Okay? Here we go. So to do the ice cream lab, you must, I said no more moaning, I'm sorry. You must be able to use math. I said no more moaning. Come on, guys. To predict whether the amount of salt water is large enough to freeze the ice cream mix.
So some of us aren't going to have good ice cream.
Why?
Or you give us all different amounts of ice cream?
No. No. But you just have to be able to do the math on the quiz tomorrow, or make it up before we do the lab. Okay? And the lab is Wednesday. All right?
Oh,
so you have to be able to answer a single question.
So tomorrow is the question.
Tomorrow's the question.
And it'll be like what we just did?
The equations are all like we've been doing since Friday. Okay? But you have to know how to apply them and how to interpret the answers to give you the answer to this.
So
Okay?
What are our materials for
The
the lab?
material for the lab? Ice cream mix, ice, salt, and water.
How many grams of salt?
We'll get to that. I'll give you all that tomorrow. Okay? And I'll give you a new list on Wednesday when we do the lab. Okay? All right. It's not hard. The lab's easy. The lab's fun. Okay? But what? All right.
So we're not going to have like a homemade ice cream mix?
No, you're not going to be cranking by hand or anything. You'll be rolling the ball around. All right. All right. So number one, I want to tell you about the ice cream mix. Okay? Let me tell you about the ice cream mix. The mix, at its freezing temperature, but will be completely liquid. So, this was the section that we filled out on Friday. Okay, that was the freezing for water. Okay, now the pattern is the same, even though we're using different values because we're not using water in the ice cream lab. We're using ice cream mix, and we're using salt water. Okay, so but the pattern of behavior is the same. Okay, now, huh? Will it still be creamy? That depends on how good a job you do making it. All right, now, so this is the region where we're talking about here. So the equation that fits this, you have to know which one to use. You have to know which one to pick. Okay? Now, notice that we have got, the way I described that here, we've got the ice cream mix cooled down to the point where it's at its freezing temperature, but it hasn't crossed the plateau. It hasn't frozen. We've got to take out enough energy to get it to freeze. Okay? Got that? All right. So it's at its freezing temperature, but it's still completely liquid. None of it has started to freeze at the point that we start, at least in our calculations. All right? And I'm going to go ahead and tell you now the approximate freezing temperature of the ice cream mix is negative 5.0 degrees C. All right. I will give you the delta H tomorrow. I don't want to tell you today. I'm going to tell you tomorrow what the delta H is for the ice cream mix. Yes, I already have it, but I'm waiting until tomorrow to give you the values that you plug in. Okay? Yeah. So there's some plug and chug math, but then you have to interpret what it all means to this situation tomorrow. Okay? The plug and chug is plug it in the figure out which equation to use, plug it in, get an answer, and then when you get that answer, you got to figure out how that fits to the question. All right? That's maybe the hard part. That's the part where your head becomes something other than a paperweight. Right? Yes. Absolute zero is negative 273.15 degrees C. All right. It has nothing to do with this lab. I'm not sure why he's asking the question. What?
Because he mentioned absolute zero in the video.
Oh, I got you. Okay. Well, on the Kelvin scale, that's zero. Okay, so let's talk about then the salt water. Now, typically when you're making homemade ice cream with a homemade ice cream freezer, you use a mixture of use a mixture of water and ice, and then you dissolve salt in the water. Of course, a lot of the salt gets left in the bottom too, but basically what's doing the work is a saturated water solution saturated with salt and the ice that continues to melt. But we won't get into all that theory. We're just going to keep it simple by going with strictly salt water here for our quiz tomorrow. Yes? Ooh, freeze faster. No, it makes the freezing temperature much, much lower. Okay, which is what I'm going to tell you here. Salt water will have a beginning temperature of negative 20.0 degrees C. Pretty cold. Okay? Saturated salt water, that is water with all the salt you can dissolve in it at its freezing temperature, has a freezing temperature of about negative 21 degrees C. So this is right just barely above its freezing temperature. Okay? During the course of our theoretical problem in the lab, in the quiz tomorrow, the salt water, this is kind of like a helpful hint here, will remain in the liquid state. Alright, so if you read these two statements here, you should have an idea of which two equations you're going to be using already. Okay? What? There's only two equations. In all the stuff we've been doing since Friday, there's only two equations. Plug different values in the equations, but the only two equations. Okay? So this you should be able to figure out which equations to use to solve for this and solve for this. Okay? The tricky part is once you get the answer, what do you do with it? Okay? There's actually one other tricky part we'll get to. First, I want to take a second and talk about what a homemade ice cream freezer is, because not everybody has made homemade ice cream. All right, so if you were to make homemade ice cream and use a homemade ice cream freezer that you go to Lowe's or something and buy, okay, they usually have this basic form. This is not the kind you put in your freezer and freeze. This is the kind you put salt and water in, huh? Yes, it'd be a good idea. So you've got a cylinder that's made of some kind of metal. Nowadays they make it mostly out of aluminum. And that cylinder then is what you put your ice cream mix in. Alright? Now, the ice cream freezer you use at home, the maker you use at home, also has a hole in the top and a paddle down inside, and it turns, that sort of stuff. But the basic idea, the basic concept behind an ice cream freezer is you've got this thing in the middle of it, okay, that the ice cream is in. Alright? Then around that ice cream mix in that metal cylinder is a kind of big bucket. Alright? And in that bucket, that's where you put the salt, water, and ice. Alright? That's what goes in there. Yes, sir. Huh? Well, the ice melts and makes water whether you put water in there or not. I typically put about a third amount of water in there because it makes it actually go a little faster when you start with a little bit of water in there. Okay? But it makes its own water whether or not. You always have a weep hole in the side where the water and some of the salt goes flying out or seeping out and stuff. Alright? Now, what happens is that this is a system where we've got a difference in temperatures. We've got a really cold temperature out here and a warmer temperature here. And what this system wants to do is equilibrate those temperatures, meaning it wants to get them to be the same. Okay? The universe wants to equilibrate everything. Okay? The universe wants to equilibrate everything. Once you understand the law of thermodynamics that deals with entropy, okay, you'll understand what that's all about. Okay, basically it's the law of entropy in thermodynamics. Okay, so the energy in the ice cream mix wants to either leave to match what's in the outside, or the energy in the outside wants to leave to match what's in the inside, so that the temperatures of the two are the same. It's the difference in those temperatures that creates the heat energy transfer. It's the difference in the two temperatures that creates the possibility of heat energy transfer. It's why weather works on the planet Earth. Okay? The Earth is like a big rotisserie. You know what a rotisserie is? Yeah, you put a chicken on a spit and it turns around like this, okay? And the sun is like the fire that's heating it up, and it's heating up whatever's nearest the sun, right? What's pointing toward it. So that side of the Earth is heating up, and the poles are cooler, and the backside is cooler, and so that difference in temperature creates this system that the Earth wants to equilibrate, wants to get the temperatures to be the same, all right? And that's what drives all the wind and rain and everything else on our planet. All the weather conditions that exist on our planet all have to do with all of that we're a big rotisserie. Okay? All right. So, which one of these Q's is going to get smaller and which one's going to get larger?